In Lesson 8, we'll be using trig identities. Some we've seen before and some we haven't. In right triangles before, we've seen that if I use the reciprocal of the sine, cosine, and tangent functions, we get cosecant, secant, and cotangent. But what we could also do is we could flip that backwards and say that the cosecant, secant, and cotangent could also be used as reciprocals of the original three. We briefly mentioned that tangent can be expressed as sine over cosine. We'll be using that a little bit more later. And also, if I take that reciprocal of that tangent function, our cotangent, we can flip that fraction and just get cosine over sine. Identity that we haven't seen before, but is based on our basic right triangle, is going to be the Pythagorean identities, as in cosine squared and sine squared is going to be equal to 1, coming from the Pythagorean theorem, where previously x was the cosine and y was the sine from our unit circle, and if I rearrange those as a right triangle, we see that that Pythagorean theorem holds true. We also have a couple other Pythagorean identities that really stem from that first one, as in if I take my original Pythagorean identity cosine squared sine squared equals 1, and divide them all three terms by cosine squared divided by cosine squared gives us 1, sine over tangent squared, sine over cosine squared gives us tangent, as we've seen from the quotient identity from before. And if I take 1 divided by cosine squared, I get secant squared, which we've said is a reciprocal identity. So I can get the rule then, tangent squared plus 1 is equal to secant squared. And that means if I take that original Pythagorean identity and divide by sine squared instead of cosine squared divided by sine squared is cotangent squared, sine squared divided by sine squared gives us 1, and then 1 over sine squared is another reciprocal, we get cosecant squared. I suggest it's a good idea to remember all three if you can, but as long as you remember that first one, you derive the other two by dividing by cosine squared and sine squared. We can use these Pythagorean identities to solve for missing trig measures rather than using a triangle as we've done from before. The second question is a little bit more challenging than the first here because it's not immediately obvious which of those three that we discussed to use. But if I notice that cotangent and cosine both show up as reciprocals in that middle function, I can use that as a starting point, but you wouldn't also be wrong if you tried to plug it into a different function if I was trying to plug it in directly into cotangent squared and then solve it a different way. Yeah, let's say if I was to use our middle function from the one we chose from above, tangent squared plus 1 is equal to secant squared. Let's start with the formula itself, and again, this is one that we would want to be able to start with on a test or quiz. We know that if we're looking at the cotangent as a given, that's actually just a reciprocal of tangent. So if I take that and plug that directly into my formula, I have the tangent value, but I got to remember to square it. So as long as I flip and use a reciprocal of 5 over 2, plus 1 is equal to secant squared theta, which we don't know yet. But once we do know secant, all I got to do is take another reciprocal, and that will find us our cosine at the end. Just got to take care of some algebra steps. So square, add 1. Equal to secant squared theta. I'm going to add fractions here, so I get 29 over 4. If I add 4 over 4 is 1, equals secant squared theta, just like any other trig function, or really just like any other algebra question too. As long as I just finish this by taking a square root, now I'm just going to have the secant by itself, and it looks like secant theta is going to be the square root of 29 over the square root of 4, which is just going to be 2. We do have to remember that we're looking for cosine, so cosine is going to be the reciprocal of that function that we just found. It's going to be 2 over rad 29. I leave an equal sign there. And if I rationalize that, we get 2 rad 29 over 29. Something we haven't mentioned yet, though, is that when I took that square root, it actually should have been a plus or minus, but that's what that last instruction that I've just been kind of ignoring until now comes in. If I know it's got to be an angle that's between 180 degrees and 270 degrees on my unit circle, I just have to remember what my cosine value would be in that quadrant, and since my x value is negative and my y value is also negative in that third quadrant, when I was using that cosine, since it represents those x values in my unit circle, that would have to be a negative for my answer. So final answer on that one would be negative 2 rad 29 over 29, using the fact that in the third quadrant especially, it's going to be negative. But if I was to solve that similar question with the same setup in a separate quadrant, could have gotten a positive answer. Checking the similar sort of work on the first one should have been a little bit more straightforward question because you have two trig functions that use just that basic Pythagorean identity, sine squared and cosine squared. But it's the same idea. You want to use the value that you're given. In this case, we're given the value of cosine. Want to plug that in, square it, try to isolate and solve for the sine of theta, which is what you're needing in the last place there. And you do have to remember that when you are taking a square root, just like the question we just practiced, it does imply that you could be positive or negative. But since we're looking at the second quadrant angle between pi over 2 and pi, like saying between 90 and 180 degrees, we know that sine would have to be positive in that quadrant. So rather than use the negative answer, we know it's got to be a positive rad 33 over 7. You can also use these properties to simplify trig expressions, and these questions are going to come in two basic types. One like this, so they appear as one term, or terms where I'm trying to reduce in terms of sine and cosine values, because those are the most basic functions we can apply to really any other kind of reciprocal. And we'll have a question like number 7, where it looks more like the one we just practiced, where it shows up as a Pythagorean identity. You want to look out for things like second powers, two terms, and that means you're using one of our new equations at the end there. Like I said, if we're looking at one of these more, I would call them basic types of questions, we just want to express everything in terms of sine and cosine to start. That's where we're going to see the most cancellations, the most way to combine these. Sine is already sine theta. Since there's going to be so many fractions working with questions like this, I just wrote that as a fraction over 1. But then secant theta, rather than expressing that as a secant, if I want to write that in terms of sine and cosine, I know that secant is going to be the reciprocal of cosine. All I got to do to combine these is basic fraction operations. Multiply across the top, I get sine theta times 1. Multiply across the bottom, I get 1 times cosine theta, so that's cosine theta. And to simplify an expression means it should just be expressed using a single trig function. And if I look up back to the top of this page is going to be pretty important for all these different rules. We know that sine over cosine can be expressed just as the tangent of theta. So that means that we have our simplified answer. It's both simplified form algebraically. There's only one term. There's no common-like terms to combine. And it's just one trig function. Next one works kind of the same, where if I notice that we kind of start the same way we finished last time, as in if I have tangent theta, that can be expressed as sine theta over cosine theta. Cosine theta is just cosine theta by itself, but just like any other algebra rule, we know that if I have like terms on the numerator and denominator of a fraction, we can cancel those out, and that's just going to give us sine theta. Again, simplest form because that's our single trig expression. That brings us to our type of question where we're going to need to use that Pythagorean identity, and I wrote that out: sine squared theta plus cosine squared theta equals 1, because we are using the cosine squared and sine squared functions on this question. And all I really have to do here in terms of expressing this in terms of one trig expression is I just got to pick one to isolate from my first trig function. Could actually be solved using either one, but I'm just going to choose to solve for cosine squared theta just by subtracting sine squared theta from both sides, just like any other algebra question where I'm trying to isolate. I can just subtract these other term, and now I have the one term that I was looking for, cosine squared. And also a lot like algebra 1, now that I know that cosine squared theta is the same thing essentially as saying 1 minus sine squared theta, because those two are equal, I can go back into my original expression, and if I need to get this down to one trig function, I can replace cosine squared theta with what we know it's equal to, that 1 minus sine squared theta, and then I'll have the rest of that equation still. So 1 minus sine squared theta, substituting that in for our cosine squared theta, but then since I still have that second term, I don't want to forget that part, I want to make sure that whole expression stays from the original. We've made our substitution, but then we just need to simplify this. Again, simplest form, just like any other algebra question, means I need to combine like terms. I just have two terms that are the same, that's sine squared theta, so this would be my simplified answer. We have a single trig function, we have our like terms combined. This is our simplest form of that expression, 1 minus 2 sine squared theta. And again, if I just chose to rewrite this using cosine squared theta, we could have a different answer, but both would be equivalent, both would be simplified. We have a question similar to that, which is next to it, and a few others underneath. This is really helpful if you're just getting more comfortable with how those Pythagorean identities work. This one's almost coming directly from the fact that we're given an equation where tangent squared theta plus 1 is equal to secant squared theta, same question that we've used from before. And then if I solve in that equation, just to try to isolate, in this case, 1 by itself, we see the expression from the actual question. If I see secant squared minus tangent squared theta, it's because I can just take that original Pythagorean identity and then just get that expression by subtracting tangent squared from both sides. Once I know that, just like in that last question, I can replace that expression with just value that it's going to be equal to. I just replace that with a 1. Then I just have an expression as simple as 2 times 1, and that final answer is just going to give me 2. Once I get down to number 8, we see an example where we don't have any second powers, no second terms. So this is an example where we want to think, how can I express this in terms of just sine and cosine? Our choice has been made for us with the first two. They're already just sine and cosine by themselves. But if we remember that tangent can be written as sine divided by cosine, and that's going to, again, create some cancellations, we just want to keep that, again, like dividing by tangent is like dividing by that fraction, sine over cosine. And all you got to have to remember from that point is that dividing by a fraction is the same as multiplying by its reciprocal. So I changed that step. We've seen a similar step to this before where I see that sine on the top and sine on the bottom, numerator and denominator, is going to cancel. And then if I just have two cosine expressions, cosine times cosine is still in simplest form if I just leave that as cosine squared theta. So question right next to it. Again, as soon as I see it, this is a second power. I want to be thinking that this is probably going to involve my Pythagorean identities. In this case, since I have sine squared theta in the question itself, first step that I would do, since we don't exactly see a 2 anywhere in this formula, is if I know that I can group the 2 out as a common factor, so greatest common factor for the numerator of that fraction. We can group the 2 out, and then if I notice what I'm left with after dividing both terms by 2, 1 minus sine squared theta, I can get that directly from my Pythagorean identity as long as I subtract sine squared from both sides. Like we have on those other questions, I see that that's equal to cosine squared, so rather than having that 1 minus sine squared, I just make my substitution step and plug in cosine squared. And like we've had on other questions as well, we're able to cancel out numerator and denominator. In this case, it's a second power and a first power of cosine. So 2 powers divided by 1 power, I'm just left with 1 power of cosine. And we don't want to forget that coefficient, the 2 in front. When we prove a trig identity on these next few, it's a lot of the same steps as what we've done from before, except the only difference this time is that we know the value that we should be simplifying this expression to is given to us on one side of that equation. So if I take my similar steps, if I see that I have a tangent theta, I want to express that in terms of my sine and my cosine values. Same thing if I have a secant, I want to express that also in terms of sine and cosine, in this case just the reciprocal of cosine. And like we've done on that last question, if I know that I can take the tangent function, sine over cosine, and instead of dividing by the fraction, we're going to multiply it by its reciprocal times cosine over 1. Nice thing again on these questions is that if we've solved them correctly, I just get sine theta because the cosines cancel out, and that's been told to us already essentially because we know that the right-hand side should be sine theta. So proving that identity is just saying that left-hand side simplifies to get you the right-hand side. Our next proving identities question, we notice some second powers and some multiple terms, so we might be thinking our Pythagorean identities again. But to get this one started, I'm just going to express this one kind of like the last one, just in terms of sine and cosine, just to see if there's any common terms that will end up canceling or combining. Let me finish the theta there. So if I was to combine these, again, I can't really do anything with one yet, but I can list this as sine squared theta over cosine squared theta, having rewritten secant as 1 over cosine squared. And similar to that last question, if I know that sine over cosine makes tangent, and since we have both of those raised to the second power, what I really have is 1 plus tangent squared. And this is really helpful to just know that we just have a direct Pythagorean identity for this. If I know that this was just a rule given from the top, 1 plus tangent squared is always going to be equal to secant squared theta, we're actually already done. So it does pay to either memorize those formulas or know from sine squared plus cosine squared theta, I could eventually arrive at this equation as well, because I wouldn't require any other steps. We've already essentially proven it. Next couple questions aren't exactly the easiest, but they are at least made easier if I remember my steps. First one being to simplify everything in terms of just sine and cosine values, just to see what's going to cancel. So if I see that if I write cosecant, that's our sine reciprocal. If I know that cotangent is the reciprocal of tangent, so instead of sine over cosine, we have cosine over sine. Cosine's already expressed as cosine, so I can't really do anything there. All I got to do on the first step is just multiply that second term together, so I get cosine squared over sine theta. And I also notice that since these fractions have like denominators, I can just combine them directly together. So I just got 1 minus cosine squared on my numerator, and the shared denominator is just sine theta. This is where it's also important to remember my Pythagorean identities. I know that 1 minus cosine squared theta is just sine squared theta, and that's again coming from our foundational, cosine squared theta Pythagorean identity. If I just take both sides and subtract cosine squared, and like on that last or previous question, I guess, if I have 2 powers of sine on the top and 1 power on the bottom of that fraction, that's just going to cancel and just give me sine theta. Again, we're reinforce that with a proof because right-hand side should come out to sine theta, given that as a hint. Last question, we want to start, again, even if it's a longer setup, kind of the same way. We know that if I write secant, that's going to be 1 over cosine theta. And again, if I was to divide by cosine theta again, that's not really going to change anything for the bottom. If I was to list the tangent theta, again, that's my sine over cosine. And this question was originally missing it, but it should have been a cotangent there on the bottom. So dividing by a cotangent means we're going to flip it and multiply by the reciprocal, sine over cosine. And here, like on the last question, if I combine the first term together and combine the second term together, I notice that we have common denominators. They're both in terms of cosine squared. So much like we did on that last question, I can directly subtract the tops to get 1 minus sine squared theta. Identifying my Pythagorean identities tells me that 1 minus sine squared theta is the same thing as cosine squared theta. And if I notice that the numerator and denominator are the same, they'll both directly cancel out and just give me 1, which again we're told from the proof is what this should simplify to anyway.